Hello, so we're gonna go ahead and get started. So this is the first installment of our speaker series for the fall, so we're super excited about that. I'm just gonna give some quick housekeeping notes before we get started. So just hold all the questions for the end. Please keep the questions limited to the speaker and topic. And yeah, so this is brought to you by CCI-CVN. We are the Central Virginia node of the Commonwealth Cyber Initiative, and we're a state program establishing Virginia as a global center of excellence in cybersecurity research. We support research, workforce development, and innovation at the intersection between cybersecurity, autonomous systems, and intelligence. And every year, CCI and CVN sponsor research experiential learning projects, and today's speaker is a recipient of that funding. So today we have with us Dr. Tianhao Wang, and it's got a lengthy resume. Let me pull it up. Um, so he is an assistant professor of computer science at the University of Virginia. He holds a PhD from Purdue University and a bachelor's degree from Fordham University. He specializes in differential privacy and machine learning privacy. Dr. Wang has over 50 published research papers and has been awarded the ACM CCS Best Reviewer Award and the Sirius Diamond Award, among many other achievements. Today, he will be sharing his insights on PPSDG, a privacy-preserving synthetic data generator. So you can go ahead and take it away.
Thank you for the kind introduction. My name is Tianhao Wang, and glad to be here to share my research and thank CCI-CVN for sponsoring this research. So I'm gonna start with some motivation. Today we live in a world with many different sources of data going on everywhere. It's great we can leverage those data, but some of the data are actually sensitive. For example, individuals' medical record or financial record. So to sort of unlock those sensitive but useful data with great utility. One very useful definition is called differential privacy. It is a mathematical kind of privacy definition, but the idea I hope to deliver to be pretty straightforward. So the idea is that we want to simulate a ideal world where any individual's data can be removed, but we still observe the output. Okay, so we have a real data set in the real world, and this is the ideal world. In the ideal world, the last user's data is removed, and we run some algorithm on it, like a query, and observe some results. And we hope the two results could be similar in a sense that we can claim that, XN was not used when we process this query or answer this query. So that sense, no one can argue or claim any sensitive information about XN. So XN's privacy is preserved. So differential privacy, the beauty of it is we can simultaneously simulate the deletion of any individual data, not only XN, but XN-1 up to X1. Okay. So this is a kind of the mathematical notion, but I hope the descriptive idea could be more informative. But mathematically, we are computing probabilities, and the probabilities are similar, bounded by constant e to epsilon. So you may ask why, how to achieve this kind of a very weird kind of a mathematical notion. So actually a very naive way called the randomized response can be used to achieve this. It was designed back in like 1965, and it was used for asking sensitive questions, but hopefully get some true answers. So the question is, for example, do you have some certain disease? And the answer is, well, we don't directly answer the question. What we do is we flip a secret coin, can assume this is a fair coin. And if the coin comes up head, we answer truth. And if it comes up tail, we answer randomly, right? So, so we can assume any individual, no matter whether they answer yes or no, there is still a probability that their true answer is yes or no. So it's their real answer is in any case hidden and protected. And also we can easily calculate the probability of a person with the disease answer yes is the probability is the sum of the two, and we can easily calculate that. And similarly for other. And then we can also prove the differential privacy bound in this case, which is we enumerate any possible v and v prime and y, because here we say for any v and v prime and for any y, it always has to be bounded by e to epsilon. So if we enumerate all of them, the largest one could be 75% divided by 25%, which is 3. So e to epsilon is 3. So the idea in this case, why we can get a useful and meaningful answer is, well, for each individual, we only see a very noisy answer. But if we aggregate many of them together, noise can be canceled out, and we can get insights from the statistics, right? So that's how we also observe many of the natural things. In more general, this is a slightly more involved, I would say, complicated mechanism, but still very, I would say, hopefully simple. So, the upper figure shows the system model for this. So we have a sensitive data, and some data analyst is interested in the data, and they issue some query, and the system can easily compute the true answer. Hopefully, it's a linear query or some query that can be easily answered. And what we do is we just add some noise to it and answer it, right? So it's super simple. We just calculate the true answer, add noise, and release the noisy answer. And this can be proved to be satisfying differential privacy. So it's a little bit different from randomized response, but still we just draw a random noise from a particular distribution here called the Laplacian distribution, and we can easily prove that. And those are some properties of Laplacian distribution, and those can be used to prove this bound. I won't go into detail, but the high-level intuition why differential privacy can work is it really is leveraging the stability, or also called the sensitivity of the algorithm. So if the query itself is stable, meaning that changing any individual record won't change the result too much, we can easily support it with differential privacy. If it's unstable, meaning if we change the individual data, the result changes very dramatically. Typically, we cannot use differential privacy on those kind of queries. I mentioned randomized response, Laplace mechanism. We can also use our favorite distribution, Gaussian or normal distribution. There are pros and cons of that. I won't go into detail, but in machine learning, people use the normal distribution more often. Yeah, there are different in terms of their properties. So there are pros and cons. One last background knowledge I want to mention is composition theorem of differential privacy. So if we have a pretty complicated algorithm and we want to sort of answer it step by step, right? Like in machine learning, we compute the gradients step by step, and we need many those of the steps. So differential privacy has a nice property of composition, meaning that for each of the step, if we can prove it is a differential privacy, and then we can compose all the steps together. This modular kind of thing is very useful when we design complicated algorithms for example, machine learning or data discovery, right? So the data analyst wants to read this, and then based on the results, have new interest and want to read that, etc. Right? So those iterative things can also be supported in differential privacy because we have this sequential composition. But we sort of sacrifice a bit because at the end of the day, the more we get from the data, the more leakage there will be, right? But differential privacy is a quantity, gives us a good quantity or amount of leakage, so we can have a good understanding of how much we have leaked. And there are, of course, more advanced one because the first one is sequential and linear degradation of epsilon, and with the advanced one, we can have like square root k degradation instead of k. And there are more research going on in this area. I'm not going to, and I'm personally don't work in this domain, but I'm more empirical or applied researcher that use those results and hopefully solve different problems. Those are sort of mostly the background, the property of differential privacy. I hope I can give a very high level introduction. And then some of the tools are super useful in differential privacy and also data analytics. One is the super simple histogram, right? So for like each bar here is age range, and we want to understand the distribution of age or whatever, and we can just do counting, like scanning the data set, and we can get those results. And we can not only do one-dimensional but multiple dimensional. Right? That's super simple. And another very useful tool nowadays is called differential privacy stochastic gradient descent. Okay, so this is anything else other than the those in the box are traditional stochastic gradient descent, and those are, we just add noise, right? So here, right? So as if you remember, I mentioned we can just add noise and the Gaussian noise to the results. So this is how we introduce differential privacy, and this clip step is for more for the ensuring the stability I mentioned earlier about the algorithm. So those just very simple but quite useful. So the research topic I want to more focus on today is about, as the title suggested, synthetic data generation. So the high-level question definition is we have an original data set can be with like a million of individuals, and they each have like attributes. So this is a very classic problem in the U.S. Census. So the census is publishing the very detailed information about the population within the United States every 10 years. And they want to protect user data, and they, of course, the easiest way is don't publish anything, but that's not useful at all. So they still publish data, but have some technique to protect user or individual citizens' privacy. So what they do originally was they use some very heuristic way, like swapping some of the the attributes or just changing, and those were shown to be broken because researchers can easily reconstruct the original data set from the synthetic one. So later, Census adopts this notion of differential privacy, so we can have a more formal guarantee of a privacy leakage. So the idea is very simple, right? So we have a original data set, and we want to generate a synthetic data set. And for this case, we just assume we have only one table in this database. Of course, census could have like, I don't know, very complicated use cases, many different tables. But for our case, we mainly focus on the one table setting. So why we were working on this was when I was a PhD student, we were doing different privacy research for a while, and we haven't seen any real world deployment. And at that time, like in 2018, the NIST organized this competition. NIST organized many different competitions. So this is their public safety division within NIST that are interested in transitioning some of the research to some of the tools they can use. Okay, so they want to host this challenge so they can like deliver this tool to like first responders, so they can do more or better allocation of their resources or whatever. So we participate in this, and this is our team called DPC. We ended up the second in the final challenge, but it was a sequence of multiple challenges. We were always in the second, but we don't know how. So the first team is from UMass Amherst, and we are the second, and the third was from National University of Singapore. So it's mostly we three teams, and there are also other teams. They are not always on the top three. Like there's a team from USC, from UCLA, from Georgia Tech, etc. And this is another challenge related to differential privacy. So after the success of the 2018 challenge in 2020, they also have it's more for the taxi trajectory data release. So I think the first one this time, well, it's not ordered, but this is from US, and the second is from UMass, and this is our team. And you see, this is Duke team. They're not super competitive, but anyway. So this it's not only about pure research, but more of it's a competition. There is many detailed things going on. So being on top three doesn't necessarily mean we are doing excellent research, right? But at least shows our research can be useful in some sense. So I mentioned this research and a problem. So naively, if you are very familiar with the machine learning, the generative AI kind of thing back then was called the GAN, a generative adversarial network, can be a very natural choice. So back then it was showing that the basically GAN-based solution doesn't perform very well, but it performs well on like image data set because it can capture the features or patterns of the image, like those high dimensional correlation, but it cannot handle those lower dimensional data sets very well. This might change nowadays, right? Because we have diffusion models and large language models. And the training paradigm also changes, right? Because previously we just train again from scratch. Nowadays, no one train any large language model from scratch, right? So things, I would say the world changes dramatically, and this statement may not hold now. Actually, we are doing some research using diffusion model as well as large language model to revisit this problem and understand what's the best way to generate a synthetic tabular data. But back then, the sort of state-of-the-art solution, which was adopted by all the three teams I mentioned ourselves, from UMass Amherst and from NUS, all use a graphical model-based solution. Those are like I would say much easier than more recent generative AI models, right? Because it's purely based on correlation information or um, uh, statistics, or it goes all the way back to the histogram I mentioned earlier, right? So because all those are based on counting. So for if you are not familiar with the graphical model, it's super easy. So each node represent a attribute. So for example, this is A1, this is A2, and each edge represent a correlation information. Right. So and if there's no edge, it means the two attributes might be independent, not not purely independent, because the transitional statistics can have some influence, but at least we don't need this edge to show some more to capture more information. We have necessary information to capture those. We don't need that edge. Okay, so and this edge can be represented as, oh, if A1 is like, say A1 is gender, and if A1 is male, the probability of A2, let's say, being age and old, right? So male and old, although you may think those are independent, let's make them correlated, right? If gender is male and age is old, what's the probability they are happening together? Maybe like 25% or whatever, right? So using histogram can capture all those information, and we can construct a graphical model, and from the graphical model we can sample data one by one, and we can construct a synthetic data set. And this was adopted by all the top three teams in all in the two competitions, and each competition is 3 or 4 rounds. So so we all use that. So some of the results. So after the competition, we summarize what we got from the competition, and we wrote a paper. Was published in Using Security 21. So it can capture results better. So those are two different data sets, and each column represent a different evaluation measurement, right? So pairwise marginal, how accurate it is, any random range query, how well we can answer those, or we train a classification model on it, how well the model performs. And on x-axis, we vary. So this is a typical way to do research in different privacy. We vary epsilon value, and on y-axis we usually measure the error. So the typical trend is going left to right, is going down. And the lower the curve, the better. So we are almost always the best. So this is pretty seen. So this is slightly different from our team name DPSync, because when we submit the paper, it's double blended. We cannot use DPSync anymore. So we just change a name a little bit. But this is our kind of research. And finally, I want to highlight after the research, I continue working in this area. So my ultimate goal is to build as the title suggests, right? So a privacy preserving synthetic data generator. So a generator, I hope, can be used for generating different kinds of data. So for example, in the upcoming MC paper, we use it to generate network traces. And last month, in using Security 22, we extended, although it's a slightly different research idea, because we, as I mentioned, changed from a graphical model technique to really the diffusion model, and we can generate a pretty high quality image data set, and we also can generate a trajectory data set, and together with Dr. Kang Shen from ECE, we are working on how to handle the case where data is from distributed either located, for example, different hospitals want to collaborate, etc. And we had also a paper on generating glucose trace, sort of a time series data. And we have ongoing work for publishing or generating medical treatment data. So there are different modalities, different kinds of applications, and I hope to generate, have a solution that can solve many of the data, sort of unlock the usability of sensitive data that were considered sensitive and not able to be used. So with different privacy, I hope we can do all of those. I think that's all for my talk. Thank you.